Guys, what we are going to do today is work with a couple examples that show the procedure for simplifying trigonometric expressions, okay? And this is going to kind of parlay itself into working inside equations, okay? So if you look up there on the whiteboard to everybody's left up there, you see an equation that says 2x plus 3 times x plus 4 plus 6 equals 12 times x plus 3, right? When you worked at something like that in Algebra 1, the first thing you started to work on is the order of operations. So you took 3 and you distributed that through the x plus 4, right? You took the 12 and distributed that through the x plus 3, right? So you started to do the implied algebra so that thing turned into being something a little bit simpler, so that you could then combine like terms and all that kind of stuff, right? The same approach is going to be taken with the trigonometric expression, is that we need to make things simpler, okay? We need to go through our implied multiplication, division, subtraction, addition, and develop a simpler looking trigonometric expression, okay? Because in regards to the algebra, we want that 3x plus 4, that 3 times x plus 4, to turn into 3x plus 12, because that is something a little bit simpler than the implied multiplication, okay? So that's kind of the plan here. I think one idea or one practice that is very important for us is to continually check our answers with our technology, and whether that's Desmos, whether that's GeoGebra, or your TI 384, or even a TI 30 can do some of this stuff. TI 30, obviously, it's easier for us to use the graphing tools because we can look at the graph and see where the graphs overlap, if they overlap everywhere. Using a TI 30 that doesn't have a graphing capability, you have to use the substitution technique to see if these things are equal. And that's an okay technique, but it's not really in the terms of like a proof. It's got holes in it, so it's not the best thing to do, but it is possible. So what we want to do, guys, is it says trigonometric identities allow us to rewrite the same expression in different ways. So it's usually in an effort to make something appear simpler in algebraic form. So in simplifying algebraic expressions, we use factoring, common denominators, product formulas, and the same is going to occur with trigonometric expressions, okay? However, we are going to obviously incorporate trigonometric identities as well, okay? And there's a lot of commonalities between a trigonometric expression and a purely algebraic expression. For instance, if I had 2 plus 3 times 4, okay, where the 2 kind of corresponds to the cosine t position, the 3 is kind of the tangent t, and 4 is the sine t, what would you do first? Yeah, you'd multiply the order of operation, because so I want to make sure we understand that thing right there, we're simplifying or evaluating, that thing right there is going to kind of govern the processes that we go through, okay? So order of operation says we need to do that first, okay? Now, leaving it in this form, multiplying those together first, is going to be tangent t sine t. So that doesn't really change anything, right? The only time that's going to change is when I take that tangent and rewrite it in terms of sine and cosine. So that's something that we're going to have to do. There's in looking at kind of a hierarchy of steps for simplifying these things, usually what you're going to try to do is kind of working back and forth with like common denominators, fractions, all that kind of stuff. But I think the initial thing you want to look at is see if there's a GCF. It's kind of like your factoring hierarchy. Is there a GCF that we can take out of all terms up there? And there's not. There's not a common like cosine in both terms. There's not a common tangent in both terms, not a common sine in both terms. So we can't do that, okay? The last, and we'll fill in some things in this hierarchy eventually, but the last thing you always kind of fall back on, kind of like when factoring, the last thing you fall back on factoring is either the quadratic formula, if it's just something squared, or P over Q, right? Your rational root theorem. So those are kind of your default, always going to work processes. What's always going to work for us if we get stuck is to change things into terms of sine and cosine. To go through and rewrite every single trig ratio in terms of sine and cosine. Because if we do that, or if we look at our list of trig identities, can't cosecant be written in terms of sine? Secant in terms of cosine, cotangent in terms of tangent, but tangent can be written in terms of sine and cosine, so cotangent can be written this way. And then tangent can be written in terms of sine and cosine, right? So every one of these 6 trigonometric functions that we use can always be rewritten so that it's showing sine or cosine, okay, being written in terms of sine and cosine. So that's what we want to do. You remember back in chapter 6 and 5, there are some questions that would say, here is, you're going to start with the sine, and we want to rewrite the sine in terms of, or maybe it was a sine squared, and rewrite it in terms of cosine, or cosine squared, and we're doing that. The purpose of that was to build to this point here, because we're going to have to do that inside these expressions before we can even address that thing. Okay? So I'm going to take cosine t. I'm not going to change it, but the tangent t turns into sine of t over cosine of t, doesn't it? So that's the tangent, that's that right there. But I still have times sine of t. So this term right here is the same as that one there. All right. Something that I think is beneficial, you can either do this at the end or you can do it kind of periodically throughout the problem, is to grab one of your graphing tools and if I've made a valid substitution here, okay, so what we start off with is cosine of t plus, let's just, so it graphs it, we use x, plus tangent x sine x, that's what we start off with, okay, and we just turned it into cosine x plus sine of x divided by cosine x, then times sine of x, oops, I don't know what went up there, times sine of x. And the idea is, if these graphs overlap, which they do, right? If these graphs overlap, we should recognize that what we have done is a correct substitution. Okay with everybody? Okay. Now, I can do my order of operations. I can now do that, right? So that turns into, what's that going to turn into? Yeah, that's going to be sine squared x over cosine x, right? Okay. Let's just see if that makes sense. If I go cosine x plus, then I write sine squared x divided by cosine x, does it produce the same curve? All three of those things are the same, right? Okay. So that's the next step here, is actually multiply these two things together. Okay. Because that's what the order of operations tells us we need to do. We do multiplication and division left to right as we see them. Okay? So you might be saying, well, then why don't you do that division first? Well, it's because I don't know what that quotient is going to be. Does that make sense? Okay, if that was like a 2 and a 4, yeah, I could reduce that to 1/2. Or if it was 6 and 3, I'd reduce that to 2. I could do those if I knew what these values were. Okay? But I don't know those values, so I can't actually do the division. Does that make sense? Okay, so then I get to the multiplication, I can do that multiplication. So it turns into cosine t plus then sine squared t over cosine t. And this is where our understanding of multiplying fractions comes into play. You multiply straight across the top and straight across the bottom, right? And that's how I generate this. Okay, so now we regenerate the order of operations And the next thing that happens, because I can't do the division, right? Okay, we already talked about that. The next thing would be addition. Okay? So now if I'm going to do addition, what two things am I going to add together here? Cosine and then the sine squared over cosine, right? If I'm going to add these two things together and they're both fractions, what do I need in order to do that? Common denominator. How do I generate a common denominator? Okay, so I'm going to multiply these two things together, right? So a common denominator is by multiplying all your denominators together. That will give you a common denominator, okay? A least common denominator is usually preferred, okay? So meaning we have to go through our denominators and take out every single term that exists that is new, okay, and apply that to my common denominator, and it becomes part of my common denominator, okay? Now, if there were, for instance, maybe a cosine squared down here and a cosine, do you remember which one we take? Like if I had just cosine of t plus over here, maybe they've got a sine of t, plus then we have a cosine squared of t. Okay, so when the terms repeat themselves, but one of them is to a higher power, you always take the one that's to a higher power, right? Okay. So if I was looking at that, my common denominator would be sine t times cosine squared t, right? So we're always thinking about trying to find that least common denominator, just because the substitutions that we're going to make with these trig identities are going to be able to be developed and recognized quicker if we're using the LCD. Okay, it's usually a little bit more demanding in regards to our algebra skills if we don't use the LCD. So here, obviously, LCD is cosine t. So we'll multiply this first fraction by that, right? Cosine t over cosine t. So I'm not changing it. I'm multiplied by 1, right? That gives me cosine squared t over cosine t plus then sine squared t over cosine t. Now you might be a person who says, okay, I don't want to go on without knowing whether that was correct or not. So you might go ahead and just go cosine x, cosine squared x divided by cosine x. And then we had plus sine squared x divided by cosine x, and just guarantee myself that that is the same curve as all the other ones were, right? Okay. So I can keep working. Now that the purpose of getting that common denominator was so that I could actually do the addition with the numerators, right? So when I do that addition with the numerators, I'm going to get cosine squared t plus sine squared t all over cosine t. All right? And now look what just generated itself. What is that numerator going to become? 1. Okay? Cosine squared plus sine squared, or sine squared plus cosine squared, is always equal to 1. That's the Pythagorean identity, right? That's essentially the unit circle there. Okay? So we get 1. Numerator turns into 1. Denominator is cosine of t. What is that the same as? Secant t. And we kind of, as we go through these, obviously they don't tell you when you're done. Okay? The judgment that we make to decide when we are done is ultimately based on the idea that we usually are interested in being able to get down to just one trigonometric ratio being left over. Okay, so something like that identifies kind of the finality of that problem. So then I want to go and just make sure real quick that we've done everything correct. So I'll go secant of x, and we see that it does indeed land on top of all those other graphs. So what's that tell us? all those algebraic steps that we did were valid, right? They were all appropriate algebra steps, okay? And we abided by the rules and properties that govern that algebra, okay? If at any time you graph one line, let's say I graph cosine x plus tangent x sine x, I graph that top one, and then for some reason I graph one that doesn't match up. It tells me I either made an incorrect substitution or I made incorrect algebra. Does that make sense? Okay. And then all you've got to do then is decide what to do next. Do I change my algebra? Do I try something different? And I think, guys, that this approach can be used using the calculator and understanding how my calculator can guarantee whether I've done things correct or not, can be an approach that you use in other areas, okay, in other mathematics. Okay, it doesn't just have to be with trigonometric identities. If I'm working in an algebra setting and I'm not sure what I just did was valid, go back a step or go back to where I know I'm okay. Type that in my calculator and evaluate at some value. Okay. Then go to the position where I'm uncertain about and evaluate that at some value. If those two evaluated values come out to be the same thing, then I'm probably guaranteed that I've done the thing correctly. Does that make sense? If they turn out to be different, then it probably means that algebra step that I was unsure about, my uncertainty was verified. Okay, there's a reason for it. And then we try something different. Okay, but there's a lot of times throughout math that you can kind of do this. Some of you took the ACT the other day, right? Last 4 or 5 questions on there, incorporate some things like this. And you were maybe uncertain about how to do it because we haven't seen them yet. Maybe using your technology could have helped with those, okay? Even though you didn't understand or know the principles that were being described, okay? So that graphical approach, guys, is ultimately kind of a proof because we're seeing that those are now, they're both red, so that's kind of stupid, but we're seeing that both of them overlap all the time, right? If you're using a calculator that doesn't have graphing capabilities, you can still do this. Okay? But I'm going to evaluate both of these at the same value. And my hopes are that the output that I get back then is the same for any value that I choose, right? The idea of this thing being an identity is that no matter what you choose for your input, your output is always the same, right? For both sides. Now, I'm going between negative 10 and 10. If I go between negative, I don't know if it'll let me go that far. I don't know, like negative, what we got, 1 million there? Yeah, okay, they got 1 million there, good. And I can check those, and we can see that those numbers are still the same, right? But is that a proof? Is evaluating or substituting a proof here with these values of 900,000? Think about from negative 1 million to 1 million. So that's quite a big set of values, right? But in comparison to the real number line, that is extremely minuscule. Does that make sense? That is a very, very, very tiny interval on the real number line. Therefore, this is not a proof because what if there's a number that lies out in the billions or the trillions or the quadrillions that would not work for that? Does that make sense? Okay? And by just testing those values, even though all of them work, there's a lot of values there that work. There's an infinite number of values there that work. There might be one sitting out there that does not work. Okay? So this is not a valid, this is not a 100% error-proof proof. Okay? We'd actually, this here, let's go back to that process, that's a proof. Does that make sense to everybody? Because we're using all values of t instead of just the ones between 1 million and negative 1 million. Okay? So that's kind of the understanding that even though I can use my technology with evaluating at particular values, and it can give me some insight of whether I've done it correctly or not, but it's not a valid, error-free, potentially error-free proof. Okay? So let's do the second one. The second one's a lot easier than the first one. Again, with this one, We've got a product of three objects here, okay? There are no like direct substitutions of anything other than our quotient identities, okay, or our reciprocal identities. So when I look at this, I can't do the multiplication, I can't simplify through the multiplication. So then what we do is we rewrite the tangent as what? Yeah, sine over cosine. Okay, so what happens there ultimately is that if that's over 1, doesn't this whole thing multiply top by top, bottom by bottom? Doesn't it turn into something like that? Does that make sense? Okay. So now what can happen with the cosine t? They cancel out. Okay. So the idea here, guys, is, cosine t, that might be like 1/2. Okay. So if I had 4 times 0.5 times, I don't know if that's, let's just say sine of t. I don't really care what the sine of t is. And then down here, the cosine t, well, if cosine t is 1/2 there, down here it's got to be 1/2, right? Numerically, we know if those 1/2 should cancel out, so they should cancel out here. The only thing is that because of that t, maybe it's 1/2 and 1/2, maybe it's radical 3 over 2 and radical 3 over 2, maybe it's 0.845 and 0.845, whatever, they're the same, aren't they? No matter what t is, they're the same. They're always going to cancel out. So they do cancel. What am I left with then? Just 4 sine of t, right? And that one, we know that is obviously just one step there, or one substitution and one cancellation step. We get down to one trigonometric identity left over. Now it's a multiple of it, but that doesn't matter. We now know that we're done. Okay, so we have one trig ratio left over. Obviously, again, graphing those things is maybe something to do. We're going to look at, well, we had 4 sine of t, tangent of t. Now we had cosine over, 4 cosine t, tangent of t, and that, man, struggling. There we go. And then we ended up rewriting that as 4 sine of x, and we do see then that those two things are the same curve. All right, so we've done ultimately a proof to show that 4 cosine t tangent t is actually 4 sine t. Okay. What I found out, guys, and obviously I didn't know this while I was in your seats as a junior in high school, but the work that we do here is going to pay off huge dividends in regards to developing your algebra skills, which if you take on higher level math classes in college and you start doing more proof work, okay, like proving why certain algebraic principles exist, like your laws of exponents and all that kind of stuff, why those exist, I think you learn a lot here that can transition into that proof work that makes that proof work a little bit easier, okay? I think the more you practice this stuff, whether you use this stuff directly, the byproduct is all those other algebra skills and all those other technology skills of checking your work get refined to where you can then use those in other areas, okay? Factoring ends up being one of those skills that ends up being very, very useful for us in simplifying these expressions, okay? When I look at this one's different than the other two that we've done because we've got now higher powers, right? Okay? When we think about an algebraic equation, that's all this really is. If we had something of the effect like x cubed plus y squared times x. Okay, do you see how that structure is kind of the same? You have something cubed. You have some sine is different than cosine, right? That's why I introduced as y. Okay, but cosine here is the same as cosine there, right? But this one's cubed, so I'll raise this one to the first. So if you had something like that, and I asked you to simplify that, what would be something that you could do there? you could take out an x there, right? Okay? You could rewrite that as x times x squared plus y squared, right? Okay? But what do we know x squared plus y squared is equal to? In the unit it's equal to 1, right? With a lot of things that we do. So what I want us to understand here is that the algebra that we've learned in the past still exists here. And often when we have sums and differences and that kind of thing, something to look at, something to think about before you make any substitutions is whether there's a GCF that exists. So what is the GCF that exists between that term and that term? Cosine x, right? Okay. So we'll take a cosine x out. Okay. Now, we have to think about what we're left over with. And remember that dividing is the same thing as factoring. So I factor the cosine x out. That means I go through here and we divide every single term by cosine x. So what's cosine cubed divided by cosine to the first? Cosine squared. Okay. What's sine squared x cosine x divided by cosine x? Sine squared x. So the cosine's a factor of 1. So I get left with that. Now what does that tell me? That's 1. Cosine x times 1 just turns into then cosine x. So if we're working inside an equation, so just let me give you a little snapshot of what we're going to see here later on. It's going to ask that. Okay. If it's asking that, then I just reduce this left-hand side to just be cosine. So I'm really asking, when is cosine x equal 1/2? And what angle is cosine x equal 1/2? Careful. Pi over 3. Okay? Or negative pi over 3, right? Okay? And that one there is equivalent to 5 pi over 3. So that's kind of the task that we're interested in later, right? Does that make sense? And just to prove that that does kind of make sense, if we go, cosine. Now here's the thing with Desmos. If I go cosine squared, it knows what to do. But I'm going to put a 3 there and see what happens. But then it was, what do we have? Sine. Okay, sine squared. It's going to know what to do with the sine squared. But when I hit enter, see how we got that kind of warning sign there? Click on that. I'll tell you what the issue is. There's only cosine squared and cosine inverse are supported. Otherwise, use parentheses. Okay? Meaning that if I want this thing cubed, I actually have to write it that way. Does that make sense? Okay. That's consistent with if you're going to use your TI 83, 84. This is how you got to type in every single sine or cosine, no matter what power you're writing it to, other than 1. GeoGebra actually allows me to type it in either way. You see in this one I typed it. Oh, actually converted it. That's weird. Usually doesn't do that. If I go cosine cubed x that way, GeoGebra knows it knows what I mean. Does that make sense? Okay. Or if I go cosine x cubed that way, it knows what to do. And if I go, I believe it even knows what I mean if I do this, even though it's kind of questionable whether I should do it that way. It knows that they all should be written as cosine cubed. So that's the nice thing about GeoGebra. We found this to end up being just cosine, right? And that's kind of validated. But now let's do this. Let's put in that pi over 3. And see what this thing evaluates out to give me. Gives me the 1/2 that we said we should have gotten, right? Okay. So we're trying to build towards that potential of solving that equation. Now, we said negative pi over 3 should work as well. Oh, there we go. Put a negative in there. Okay. Now, here's my question. How come it doesn't matter whether I put a negative there or a positive there?
Because it's just evaluating at the same thing.
Okay. Don't we know that the cosine of a negative angle is equal to the same thing as cosine of that positive angle? So that cofunction kind of properties existing there, which I think is what you're saying. If we go, because of the coterminal angles, if we put 5 pi over 3 there, still going to give us 1/2, right? Okay. So eventually finding those additional answers of negative pi over 3 or 5 pi over 3 or 11 pi over 3 would be the next one. I guess actually the next one is going to be 7 pi over 3 and then 11 pi over 3. But those processes of finding those additional answers, we'll talk about when we get to those equations. But it's ultimately the symmetry of the unit circle. Okay. So when you see powers greater than 1, look for GCFs. And then usually if a GCF exists, then it's going to simplify down to something like sine squared plus cosine squared, or it might be tangent squared plus 1, or it might be secant squared, which we can use then one of our Pythagorean identities to substitute. Okay. This one here, these tend to be the ones that people struggle with the most. Okay. Because what's going to happen here initially is this thing's going to start looking pretty ugly. But then after a few steps, things start to cancel out, things start to work out real nice, and we get a really nice answer here at the end. But why people struggle with this is because if I were to ask you what is one thing since 5th grade that you do not like operating with inside a math class, your answer would probably be what? Fractions. So here we're going to get fractions. We're going to get fractions inside fractions inside fractions. Okay? And we have to be able to understand how the order of operations, how PEMDAS, asks us to operate within that. Okay? If we can't remember those rules, those properties, we're going to struggle. Okay? Now, on top of that, what compounds that issue is that these sine, cosecant, and cosine terms are abstract to us. Okay? If you can understand how to do this with numerical values, it might make the process a little bit easier. So let's kind of think about it this way. If I knew sine, let's say sine was, it's not going to evaluate, sine will never evaluate to this, but let's just say that this term here was like 3. Minus then this term. Now, cosecant, I know that cosecant is 1 over sine, right? So let's say that this was 1/3. Does that make sense? All over something different. Cosine theta is something different. Let's say it was 5. If you had that algebra right there, would you be able to do that? Walk me through the algebra here of being able to simplify that fraction. Okay, so you would isolate the numerator, right? Because there should be parentheses around that, correct? Okay. Based on what we learned in Algebra 1, if we've got operations occurring in our numerators and denominators, we focus on that numerator. Even if there's no parentheses there, we have to realize that there are implied parentheses there, and you work through your order of operations in that numerator. Then you would do the same thing for your denominator. Now, it's trivial here for our denominator, but you would go through the order of operations here. So if I'm going to go through the order of operations here, what would I end up doing first? Okay, I would subtract, but you would rewrite that 3 as 9 over 3, right? You'd find a common denominator. Okay? And then we would go and rewrite that as 9 minus 1 over 3, and that becomes 8 over 3, right? If you can do that process with numerical values, it's the same thing here. Okay? If I'm going to rewrite this, it's going to be rewritten as sine of theta minus Okay, now because there were no powers bigger than 1, I'm not going to factor anything out, so my task is to write this in terms of sine and cosine, right? So what is cosecant the same as? 1 over sine. And now my cosine, there's nothing to do down there, so it just gets rewritten the same way. Okay, so this is analogous right now to us having this written as 3 minus a third. Okay, see how now it's an object minus its reciprocal? Is this an object minus its reciprocal? Okay, we come up with, down here, we turn that into 9/3, right? Common denominator. What's the common denominator in this numerator? Sine. So I'm going to multiply the bottom here by sine of theta, and multiply the top by sine of theta. What's that going to turn this top into? Sine squared theta. Okay? So now we could have, down here, we could have changed that to, what, 9 minus 1 over 3? So I'm going to rewrite this top. The tablet died. Come on. There we go. I'm going to rewrite this top here as sine squared theta minus 1. That's doing that algebra right there. All over sine theta. Is that okay? And now the bottom is still cosine theta. It's getting better. Okay? And think about why it's getting better. When we started in the original problem, we had a difference. We had 2 fractions being subtracted, right? Look at what we have now all the way on the right. Now we only have 1 fraction in the top. Does that make sense? Okay, so it is getting better. Now, that 1 fraction that is red up there, it looks a little bit more complex than either of the fractions we started with. But the idea of this being simpler is based on the number of fractions we have, not necessarily what comprises those or create or is making up the numerator and denominator of that fraction. So now we have what we introduce here, something squared, right? Okay, when we introduce something squared, hopefully that triggers a response or a light bulb goes off, and we think that we have, because it's sine squared, maybe we can do something with this thing. Okay, so occasionally, guys, you're going to have to go to the side and do some scratch work to see if there's any applicable substitutions that you can make. Okay, is there any way that I can take that blue phrase, sine squared plus cosine squared equals 1, and transform it so that it looks like sine squared theta minus 1? Yeah, I can get that 1 on the other side, right? I can move this 1 over here, but what would I have to move to the other side to get just sine squared minus 1 isolated? Right, those two things are going to switch spots. So it's going to be sine squared theta minus 1 is now equal to negative cosine squared theta. Okay, so even though our Pythagorean identity is sine squared plus cosine squared equals 1, inside that is encapsulated a series of other true identities that we can go through and find just using simple algebra. Okay, so now let's make that substitution. Instead of writing it as sine squared theta minus 1, let's rewrite this numerator right here as cosine squared, negative cosine squared theta. It's going to be over the top of sine of theta. And now this bottom fraction is still cosine theta. Okay. Now that bottom fraction, it's written as just one object, right? But it is a fraction, correct? Every fraction can be written as itself over 1. So that's what I think it's very important for us to do that, because I want to make sure that we don't get this confused. Let's say that I don't want this idea to exist. Does that make sense? Okay. I want to make sure we understand that this bottom fraction is the cosine theta over 1. Now, how do I take a fraction and divide it by a fraction? Multiply by reciprocal. So I'm going to take 1 over cosine theta. Okay, so this wipes away. What's going to happen here? That cosine is going to cancel with one of them in here, right? So you're left with negative cosine up top. On the bottom, you're left with sine. All right. So now, think about what we did. We've just transitioned from the difference of two fractions over a fraction to now just one fraction over a fraction, now to just one collective fraction overall, right? But what is cosine divided by sine the same as? Cotangent. And one's positive and one's negative, so it's negative cotangent. Okay. Negative cotangent t. Okay. Or I guess theta. Let's see if that's appropriate. Let's see if that is an accurate answer. So I got a sine of x the one thing, if you're going to use your TIA3, does my TIA3 have a cosecant button on it? No. So on my TIA3, actually I type this in as 1 over sine. Does my TIA3 have a cotangent button on it? Nope. So I'd actually have to type this in as negative 1 over tangent. So that's kind of a pain in the butt, but it is doable. So are these two things the same? Okay. Could I also do this? Because of our co-function identities. Could I do that? Could I take that negative and put it inside my argument? I can't. Okay. Is that something we usually want to do? No. We usually like our argument to be a positive. But I mean, somebody that comes up with something on your tests and quizzes are handwritten, right? If you wrote cotangent of negative x, I won't give you credit for that. That's right. Okay. Now, what they try to do a lot of times on tests and WebAssign, so that, obviously I don't want to sit down and grade these and have 40 different answers that are all right. Does that make sense? Because then I actually have to do the problem 40 different times. What I will do is say, with my directions, rewrite this or simplify this expression so that one trigonometric function is left over and it has a positive argument or something like that. And if I say it has a positive argument, it eliminates the person writing it as cotangent negative x, right? Okay. So those are just things to think about. The directions hopefully are going to guide you purposefully in getting an answer that is then consistent with what your neighbor's answers are. What eventually happens, we're not going to do any more examples, we don't have time, but I do want to kind of explain this process here to us, or this type of problem, and then on Monday we'll pick up and start doing these. It says proving trigonometric identities is a similar procedure to simplifying. We just simplified kind of the left-hand side of an identity, or the right-hand side of an identity, okay? It says, however, we usually deal with a more complex side of an identity and attempt to simplify it down to an expression that mimics the other side of the equation and creates a known identity, okay? So here's the idea. If I started with this expression, or this equation, 2 times x plus 4 equals 2x plus 8, and I asked you to prove that that's an identity, okay, you would take one of the sides that you think is more complex. And usually we choose the side that's more complex because there's more algebra to do over there. Would you agree that there's more algebra to do on this left-hand side than there is on the right-hand side? So I'm going to do that. I'm going to choose this left-hand side. I'm going to try to alter that. I alter it, I get this. Did I get to a stage now where the left-hand side is identical to the right-hand side? So I've then proven that that thing's an identity. And that's what we do with things like this here, which we'll start with on Monday. But which side of that equation looks more complicated, the left or the right? The left, because there's more algebra to do over there, right? There's the distributive property existing there, and that's probably all we've got to do there. It's the distributive property, maybe one substitution. That's going to allow us to see that we do end up with sine squared on that left-hand side. Does that make sense? So we're gonna start there on Monday. But it's ultimately, you know, when I ask you to simplify this side, is that just the same thing as the first 4 problems we just did? Yeah, and then our hope is that when we do that, it turns out to be sine squared, and then we're done. Okay. We'll go back through on Monday. We'll read the green chart up there. It talks about some kind of strategies for you to think about in regards to these types of problems. But that'll be the process for the next couple of days, is working on more and more of these examples. If you get stuck with this stuff, guys, please use the resources on my website. There's a lot of videos, a lot of examples that you can look at to get better at these things. Okay, and that's, you know, that's how you're going to get better. Okay, there's not a magical potion or formula that says this is how I have to do every one of these. Every one of them is a little bit different. At the same time, everyone's a little bit similar. You remember going through geometric proofs? Geometric proofs, they started off to be kind of hard, right? But if we started to understand there were patterns that existed, okay, even though each problem was a little bit different, there were still patterns that existed within them that we could replicate, okay? And that understanding helped us then get through some more maybe kind of authentic proofs, things that were different from the previous ones we did. Same thing happens here. So the more you see of them, the more those patterns kind of come to light, and you can then repetitively use those in other problems, okay? But if you only do the ones that we do in class or the ones that are on homework, you're probably going to overall struggle with this stuff. So we got to do a little bit of extra. A lot of videos on my website. If you end up exhausting all those and need more, let me know. I can find you more. Do a quick YouTube search. You can find your own. Okay. There are thousands and thousands and thousands of them out there that you can find. A lot of times you can go to like Google and just type in trig identity PDF. And you'll probably see a lot of worked out examples from other classes, other
or on the academic
professors
team.
and teachers.
Please report to the gym during Wildcat time today for the yearbook picture. Again, that is gatekeepers and the academic team.